行，那我们要不就先开始，好吧
Yeah.
？OK，Okay, so good morning, everyone. Welcome to the 69th Open Seminar in Frontier of Nuclear Physics. This seminar series is organized by the Institute of Modern Physics, the K-Laboratory of Nuclear Physics and Ion Beam Application, Fudan University, and the Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. It is also sponsored by the program of introducing talents of display of two universities, the Journal of Nuclear Science and Techniques, and the next trend on the share.com. Today, we are very pleased to have Professor Fuqiang Wang from Purdue University to give us a talk on the observation of universal expansion anisotropy from cold atoms to hot quark-Gluon plasma. Dr. Fuqiang Wang is a professor of physics at Purdue University and Huzhou University. He is a high-energy nuclear experimentalist and a member of the Riksdag, CMS, and NICA MPD collaborations. Currently, he conducts backstack experiment at BN, and he worked on many areas of research in heavion physics. His latest interest is in the experimental search for the current magnetic effect predicted by the quantum QCD. He was elected a fellow of the APS in 2010. He received his PhD from Columbia University in 1996 and worked as a postdoc at RBA before joining the Purdue faculty. Okay, now let's welcome Professor Wang. Please.
Okay. Thank you, Jay, for the introduction, and also thank the program committee who invited me to give this talk. So let me share my screen. Let's see. I have something. Hold on just a second. Okay, now this should work. So you can see my full screen, right?
Yes.
Okay, good, very good. So today I'm going to talk about something that is a bit different from relativistic heavy ion collisions, but it's motivated by heavy ion collisions. I'm going to report an observation of universal expansion anisotropy from cold atom systems to hot quark-Gluon plasma. The outline of my talk is this. I will first motivate this work, and the motivation is the Azimuthal anisotropies that are observed in relativistic heavy ion collisions. I will give a brief status of experimental findings, and also discuss the theoretical understanding, or rather non-understanding, of anisotropies, especially in small systems. And then I'm going to go to the second part of my talk, and that's the main part of the talk, really to how to address anisotropy experimentally and systematically. And the tool that we use is using cold atoms. So it's kind of an emulator for heavy ion collisions. And I'll show you the results that we obtained, and then conclude. So we know that especially elliptic anisotropy is very common in heavy ion collisions. It has been observed from the very beginning of heavy ion collisions at very low energy, and that's the left cartoon shows when these two nuclei pass each other slowly. Particles are being produced. people observed a squeeze out of particles, more particles in the vertical direction perpendicular to the reaction plane than in plane. And the understanding was that the particles that are produced blocked or partially, part of the reason is that particles are blocked in the horizontal direction by the spectators that are still in place. And therefore you have more particles in the vertical direction. Of course, there are other reasons, physical reasons. So this is called squeeze out. And when you go to higher energy, like energy at a RIC, and as we all are familiar with, the system, the spectators are gone quickly because they are really moving at the speed of light. And you create something in the middle, and we think this is the Quark-Gluon plasma, and this Quark-Gluon plasma has very high energy density pressure inside, so this will expand into the vacuum in the surrounding. So you have expansion, and because you have this anisotropy in the geometry, this expansion is anisotropic, and therefore at the end of the day you get anisotropy in the momentum distribution. Let me give me just a moment. Something is blocking my screen, so let me do something here. So, okay. All right, so it's better. Sorry about that. It is a conversion from initial spatial anisotropy to the final state momentum anisotropy. Now, in order to have anisotropy in the momentum space in the final state, you have to have interactions among the constituents. Because if you don't have interactions, then because the momentum space distribution initially must be isotropic, because there is no preferred direction, the constituents or the stuff don't really know the impact parameter at that point. So you have to have interactions to know that initial information. So the anisotropy that we measure at end reflects the pressure or the energy density in the middle, and therefore consequently the pressure. The higher the energy density, then the stronger the interaction magnitude that you can expect. So we quantify this anisotropy with the V2 parameter, which really characterizes the difference between the x direction, which is the impact parameter direction or event plane direction, and the vertical direction, y direction. So this difference between x and y, the magnitude is 4 times V2. Now this is now excitation function of the V2 measurement, and at low energy the V2 is negative, meaning that you have more particles in the vertical direction. When you get to higher energy, which is relevant today, you get positive V2, and this V2 increases with energy. The right figure shows an early work by Poscancer and Voloshin. They compiled the V2 over epsilon2 ratio of the data that were available, and this was just a short time after Rick and on. So this is as a function of the multiplicity density per area, and this reflects the energy density of the QGP, if you will. And you see a steady increase and this is different centralities in goal-to-goal collisions. When you get to more central collisions and higher energy, then you have a larger energy density. So the right side of the plot. You see, and the bars are the hydrodynamic limits or predictions. We call them limits because hydrodynamics are really describing infinite amount of interaction, or ideal hydro. And as you can see, when you get to top Rick energy, actually the measurements is approaching to hydrodynamic limit. At lower energy, In peripheral collisions, it's still far below hydrodynamic limits. So this is quite exciting. So this is the first time that data reaches hydro prediction. And this is exciting because this tells us that the interaction must be very, very strong. Ideal hydro means zero mean free path, infinite interaction strength. And of course, that's just an idealization. It's physically impossible. You have to have viscous hydro. The viscosity characterizes the inverse of the interaction strength. So the lower the viscosity, the larger the interaction strength. And there's a quantum limit on the viscosity. The viscosity over entropy density ratio has to be larger than 1/4 pi. And from measurements and hydro calculation comparison, and this is work by Huizhao et al., we see that in order to describe data, you have to have a very small viscosity over entropy density ratio, close to the limit. So therefore, that led us to conclude that RHIC has created a nearly perfect fluid, Quark-Gluon plasma. And as you all know, that anisotropies are ubiquitous and exist in small systems, even in proton-proton collisions. This is only a small set of plots, measurements, and as you can see that anisotropies are everywhere. Now I have to put out cautions here, right? Especially in small systems. There are non-flow effects, and people try very hard to remove non-flows. There are various ways to reduce, mitigate non-flow, or eliminate, ideally, non-flow. Now, in small system collisions, there's another thing called trigger bias or multiplicity bias. For example, in proton-proton collisions, if you insist on very high multiplicity, you are likely getting jets. So you are biasing towards events with jets. If you require higher and higher multiplicity, you are insisting on larger and larger energy jets, or even multi-jets in the events. Now, it is very peculiar that the V2 measurement is rather multiplicity independent in small systems. And that is very mind-boggling, because you would expect that it should depend on multiplicity, because the higher the multiplicity, naively thinking you get higher densities and therefore stronger interactions. But the V2 is rather insensitive to the multiplicity. This is the V2 higher order V2 measurements. Now, multiplicity bias is severe in small system collisions, especially in PP. In PLED as well, less severe. In heavy ion collisions, it's probably not a big deal, big issue in very high multiplicity collisions, very central collisions, because it's even in very central collision, you're still, if you consider heavy ion collision is a combination or mixture of many proton-proton collisions, you are basically collecting a bunch of minimum bias proton-proton collisions. Now, of course, this is a quantitative statement. If you insist in higher and higher multiplicities, then eventually you are insisting all the proton-proton collisions to have high multiplicity. Now the cross sections is very small. So in heavy ion collisions, even in ultra central collisions, I don't think we're biasing towards many PP collisions producing jets. Now we try to move away from this multiplicity or trigger bias by looking at the centralities defined by the ZDC. Right. So we look at central collisions and the peripheral collisions of d Gord, but using ZDC as a centrality. And this plot is just the Fourier V2 as a function of delta eta. And of course, the middle peak is non-flow, jets contribution, resonance contribution, and so forth. Now, if you go to larger delta eta, the non-flow is minimal. And you actually don't see, I mean, error bars are large, but you don't see large difference. We don't see any difference between central collisions and peripheral collisions. And that's very, very strange. All right, so let me get to an idea by Wei Li a few years ago. So the ultimate small system, the collectivity in a single jet or a single proton fragmentation, right? And you can imagine that if you have a huge multiplicity in this single jet, then you will have interactions among the particles, among the constituents, and you may expect collectivity. And actually, CMS observed something that is really intriguing. That you go to the jet axis, right? So and look at the transverse direction, and you measure the two-particle cumulant V2 with large delta eta. Plot that as a function of the multiplicity in the jet. When you get to about 80 particles, you see kind of this V2 parameter goes up, or larger than a model calculation, like I think from Pythia or Pythia. That you see deviation, and this may be an indication of collectivity in a single jet. Now, Wenbin, Ziwei, Xingnian, they did calculation using MPT, and they found that in order to have something like this, you have to have interactions among the constituents in the jet. So we have anisotropies in heavy ion collisions. That's very familiar. And we have anisotropies in small systems, and even in small multiplicity collisions of proton-protons and proton-lead, deuteron gold, proton gold, helium-3 gold collisions. You see anisotropies everywhere. Now, this is the heavy ion geometry, of course, and we always think that the expansion gives you this anisotropy, and this may be true in central heavy ion collisions, in peripheral heavy ion collisions, and in small systems. It's a leap of faith to believe that. It might be true, but it's also likely untrue. So expansion would give you anisotropy, but so-called kind of escape mechanism would also give you anisotropy. No expansion, no collectivity. It's just that the particles along the event plane direction are easier to get out because the stuff is thinner than the vertical direction. So some of us kind of come up with this escape mechanism, and think at the beginning we were very, very puzzled by the data and the simulation results that we got. So I still remember many days of discussions, and we get Ziwei to Purdue for at least twice, maybe more than twice, 3 times, and we realized that actually, well, you can get anisotropy V2 even without interactions, and that is really the surface emission scenario. And that you have particles coming out, and those particles just more easily to come out along the x direction, or more probability for the particles to interact along the y direction, and therefore you have this anisotropy. Even you look at the particles without any interaction, you get a V2, and then the particles which do interact once, they actually have more particles along the y direction, and after one interaction, those particles change directions and become random in azimuthal angle. So therefore, you're converting, so to speak, a negative V2 into 0 V2. So effectively, at the end of the day, you get a positive V2 just from that. without any collectivity, without any expansion. We actually do a calculation of AMPT and even MPC, monos parton cascade. We artificially increase the cross section because we want to increase the interaction strength, and even you increase the cross section by a factor of 10 or more, you still have a fraction of the V2 that is coming from those escape partons. And you can get rid of it because you have a surface, and therefore you always have surface effect. It can get to approach to zero symptotically, but you have to have very large nuclei in order to do that. So this is kind of intermediate heavy ion collisions, 7 to 8 Fermi. Hirano would tell you that there's always a corona effect, a periphery effect, right? Because you have two nuclei colliding with each other, you always have the surface, and therefore you always have hadronic contribution. And his calculation tells us that, or shows that, it's at a multiplicity density of say 30, you get half and half. Basically, half from corona, half particles are from corona, and half of the particles are from the core, the central region. And it's more severe, of course, in PP collisions. Okay, I'm sorry. So these are all PP collisions, P-lead collisions, and the squares are lead-lead. Okay, so lead-lead is mostly core, but for small collisions, you can get large fractions of the corona effect. Right. So I would say that it's not clear what the measured V2 is. What is the physics origin of the V2 in small systems? And of course, this is a quantitative question, and you can push that to heavy ion collisions, right? That there's always something that may be different from hydro, or some contribution that is not hydro, right, in heavy ion collisions. We all agree that heavy ions, especially central heavy ion collisions, are probably dominated by hydro collective motion. Now, I didn't really talk about the energy dependence, but the V2 actually is rather insensitive to energy. Once you get to above several GeV, AGS energy, you get a V2 that is more or less as same as the top Brugge energy, and that is very strange, right? If everything is hydro, then yes, you would get the similar V2. The actual hydro predicts different V2, but you would expect that when you go to lower and lower energy, you have less and less contribution from hydro. It's rather problematic to push hydro to small systems. Okay, core corona effect, mean free path is comparable to the system size, not much smaller maybe. There's a huge non-flow and jet contribution in small systems, so we have to be careful to interpret data or remove non-flow contributions. And in small systems, the anisotropies are rather multiplicity independent, and I tend to call those Fourier coefficients. And Fourier coefficients have no multiplicity dependence. Now, in small systems, the RAA nuclear modification factor is consistent with unity. No evidence, at least no strong evidence of jet quenching in those small systems. Now, we do have to rely on model calculations to extract physics, but it's always unsatisfactory, right, to have to rely on models to interpret data measurements. Can we experimentally demonstrate collectivity at work or the lack of? And one thing that we can do is to use cold atom systems. And this is not new idea. And I will show that on the next slide. The advantages of cold atom systems are that their interactions can be tuned with external magnetic field. and their initial conditions can be manufactured. And you can control the system size, you can control the number of particles to some degree, and therefore the particle densities or the atom densities in the system. So it's really nice to have this so-called emulator where you can control a lot of things which you can control in a real heavy ion collision. The strong anisotropy, strong elliptic anisotropy has been observed in cold atom expansion 20 years ago. And people were convinced that the expansion is really hydrodynamic. And you can do an back of an envelope calculation to convince yourself that this is really hydrodynamic expansion. And this is because the cold atom system is prepared in such a way that you tune the interaction to, and I will say that later, you tune the interaction, you tune the magnetic field to reach the maximum interaction strength, so-called Fishback resonance. So you can have a large cross-section between the two atoms or between atoms in the cloud. And in their experiment, the density is about 50 atoms per micrometer cube. And the mean free path is about 0.2 micron. So the system size is about 20 micron, and therefore the mean free path is a lot smaller than system size. The ratio of system size over mean free path is about 100. So on average, each atom will have to collide with other atoms or interact with other atoms 100 times before getting out. This system must be hydrodynamic. Now, in heavy ion collisions, actually, if you use a model to calculate the mean free path or the number of collisions each particles or each proton suffer on average, in small systems, in d-Gold collisions, it's on the order of 1. Therefore, it is really a dilute system, if you will. But we do observe anisotropy in those systems. And the question is whether this is hydrodynamic, right? So you want to use a cold atom system to emulate your collision. A small system, naively, you want to say that, oh, just a few atoms. Let's just create a system of a few atoms and let it expand. And actually, just recently, the Heidelberg group, the cold atom group, did just that. They manufactured a system with only a few atoms, a few pairs of atoms, spin up, spin down. So you have interactions between the opposite spins. So that's the picture from their experiment. Okay, so this is 5 pairs, so 10 atoms, and they prepared them in this shape, anisotropic elliptic shape, and let it go. Let the trap release the trap, so let the system expand, and they did observe something like that. Now this is of course an average of many repetitions, and the dots, the dots indicating atoms, and that's just drawn on there to indicate the atoms. What they really measure is a density profile of many events, averaging of many events. And you do see expansion from their experiment. It's kind of neat. Actually 8 years ago, 7 7 years ago. So we wanted to do this experiment to examine the physics ideally, or possibly examining the physics mechanism. We set up this, and this is mainly work by Li Ke. So we were fortunate to attract him from Singapore to Huzhou University in 2017, in the fall of 2017. So we spent 5 to set this, and it's rather, I'm proud of the achievement, because this is really kind of a single some delays due to the COVID, and this really took 3 years, which is longer than we expected. But during this time, actually, we prepared a lot of things. So actually, the subsequent progress was very fast, was faster than normal, than other groups. We spent 1 year to cool down the atoms, and I will say more later. So this is just kind of give you the timeline. We observed the cold atoms, trapped cold atoms, in 2020, end of 2020. We set up an automatic computer system to do the experiment and to do data taking and analysis. And then we cooled the lithium-6 atoms further using optical dipole trap, and we were able to get to a temperature of 1 microkelvin. And since 2022, we did experiments, and I think it's we started like at end of 2021, and we spent about a year to do measurements systematically, and then prepare a manuscript. And in 2023, we did further work, and I will not talk about those, only briefly mentioning them at the end. But let me go to the setup. So this is a picture, and lithium-6 atoms, or the lithium-6 material, is heated here, and the lithium-6 atoms were evaporated from this oven, and this is a high temperature at almost 300 degree, something like that. So here is high temperature, and then the atoms are collimated, or the stream of atoms are collimated here, and slowed down by so-called Doppler cooling using lasers. And this is so you basically shine laser onto against the motion of atoms, and when your laser frequency is good, matches the energy gaps, then the laser, a photon will be absorbed by the atom, and therefore the atom is slowed down because it absorbs the momentum of the atom. Of course, this atom is now at the excited state. It will emit photons, but it emits photons in all directions. So therefore, through this process, you achieve a slowing down of the atoms, and then it's further being slowed by the Zeeman slowing mechanism, using a magnetic field, a gradient magnetic field, and a laser, using also the resonance, the frequency matching to slow that down. And eventually, they are trapped by the magneto-optic trap, basically a magnetic field a gradient magnetic field, and a lasers. I think several lasers, 4 lasers. So the laser and the magnetic field create this potential well, and now they're trapped in the well and happen to have large velocities. They will escape that potential. Like Kelvin. And you use another laser to cool the atom potential well, but it's really shallow. And then this is called the last stage is called evaporative cooling. Basically, the high speed or the higher energy atoms escape from this potential. So what's left there is really low, small kinetic energy atoms, or effectively low temperature. So this is a picture that we took. The little bright dot here is the atom cloud that is trapped in the potential. Now, how do we tune the interactions? Now, the interactions happen only between opposite spins. Okay? You use a magnetic field, and the spins, has interaction with the magnetic field, or has an energy level splitting between these 2 spins. And now you use a laser. So you create you use the right frequency to match that energy gap, and therefore they interact with an exchange of the photon of the right energy. So this is tuned by the strength of the magnetic field, the Helmholtz magnetic field, which is rather uniform. What's plotted here is the scattering length between the atoms as a function of the magnetic field. So the scattering length is very small at the small magnetic field, and also small at larger magnetic field. And at this magnetic field at 34 Gauss, you have created a resonance. So the scattering length is very large, or the phase shift is half pi basically. And the cross section is given by this, and when the scattering length is large, then it's unitarily limited to this value. K is the wave number or the moment number of the atoms determined by the temperature, and this is about 0.1 micron square. So the interaction can be tuned, and if you just tune away from this magnetic field strength, then the interaction is gone basically, right? Gradually, but quickly disappear. We measured the number of atoms in the 2-spin state, and they're more or less equal number of atoms, and this is measured through imaging in the optical dipole trap. Okay. So now the experimental results. So what we did is basically we let did not say it here. So we have two lasers cross at an angle, and now you have a trap here, and because they cross at an angle and they're not perpendicular to each other, therefore the cross area is an elliptical shape. Okay, and now the aspect ratio of that ellipse, or the eccentricity of that ellipse, can be controlled by this angle. Okay. Now we really can't control this very much because the apparatus is limited in terms of the space So we can really go to very large angle, but we can do some variation in the eccentricity of the initial trap. And then we just we release the trap. We turn off the magnetic field. We let the atom expand, or the cloud expand, and then we measure things by taking pictures. Okay? And the camera is here. Okay, and once you take a picture, the cloud is destroyed, and you have to repeat. So so you have to automate the process. So this is the result, and this is the main result. Okay, and I'm going to explain this. We took pictures. We had the two initial eccentricity or aspect ratio. This is a large aspect ratio, and this is a relatively smaller, large eccentricity. We let it expand, and you take several pictures actually, and you see that it expanded in the short axis direction, much in the long axis. Okay, we analyze the picture or the density profile, them Gaussians with we plot the size as the function of the time. Okay. And the blue is the short, and it does not change much. The red is the blue is the long axis. And it's about 100 micron to start with and end up with 100 micron. So it does not expand at all. And the short has expanded a lot, from 10 micron to 200 micron. Okay? And it's almost linear, which means that the velocity is more or less an asymptotic velocity. So your measurement is asymptotic velocity at the end. And slope, you can extract the velocity. And we also, so this is at the Fishback residence point magnetic field. So here you have very strong interaction. We also did it in another magnetic field where the interaction can be neglected, and you take pictures in the same way, and you really see ballistic free streaming expansion. This is not, free streaming expansion. And you can track the velocities in the two directions, and since the velocity are similar to each other, or they are really parallel to each other at the end, asymptotically, therefore V2 is 0. Yeah. Depending on the field. So we plot the of the magnetic field here. Okay, so the magnetic field, the V2 is 0, and then quickly rise, and then kind of saturated. Okay, resonance magnetic field is around here. At 34. Now, the beam crossing angle or the laser cross give you two different eccentricities. So first thing to do is to normalize by the eccentricity. Okay, the beta is just the aspect of the initial trap. So you normally that we can change the interaction strength. Therefore, we can change this opacity. We can change this number of interactions. Now we do a calculation, and this is a simple calculation. Basically, we can or the next atom encounters coming out of the origin, the center of the atom cloud. Okay, anisotropic. You have to do angle every So this is now a few pictures, and you observe a transition from the across kind of intermediate step. So you have basically you start with non-interacting gas, for instance, right? And then or it's dilute, so interaction is very small. And then when you cool the system down enough, then the atoms will pair each other because they're fermions, and the spins are going to pair each other, and this is through the Cooper pair, basically Barting Cooper Schiffer mechanism. Atoms, right? So those are now bosons, and you get condensation of those bosons, those molecules, and it's kind of neat. And in terms of heavy ions, we plan to do triangular flow. We just need to create this initial triangular shape, and we can also do. We think we can do spin orbital coupling between the atoms, and then see what we get from this system. So with that, let me just summarize a rather short summary. So anisotropy in heavy ion and small system collisions observed everywhere. The physics mechanisms are not completely understood, I would say. Cold atom systems offer a unique tool with tunability and controllability of interactions and the conditions, the experimental setup, the experimental conditions, the initial conditions, for instance, the shapes of the cloud, and also the densities that you can change, you can control. In this first experiment, we have observed a universal expansion anisotropy as a function of interaction strength from cold atoms to hot QGP, and we observe a smooth trend, but rather two distinct regions, quick rise and then kind of a shadow increase. If I want to be bored, we may be talking about a phase, two phases, okay? And it's not a but you never get a sharp turnover like this. But this might be a first order phase transition, and this would be the order parameter that you measure. And of course, if that's true, right? You have two phases, and these are very different. You have hydrodynamics, a liquid, right? And then you have at very small interaction strength, you have a gas, basically, non-interacting gas or minimal interacting gas and a liquid. So there's probably a lot more to learn from this, and the advantage is that you can control things, so you can do things in a way that it's easier to interpret or illustrate. So with that, I stop here. Time. Brief for questions.
Okay. So okay, thanks. So now the seminar is open for questions. If you have questions, please raise your hand.
Yeah, Fuqiang,
Hi.
very comprehensive talk. So about the hydro, you said to apply hydro to describe the small system.
Mm-hmm.
So but on the other hand, for very small system, there's some kind of collectivity. So how to how to accommodate these two these two things?
Yeah, I think so. One way to explain this is that in small systems, you have to have interactions. Without interaction, you're going to have isotropic distribution. So provided that we've taken care of all non-flow, and what do we measure is really the global anisotropy in small systems. Then the obvious explanation to me is that in those systems you have some interactions, but not strong. Just some interaction, and just a little bit of interaction would give you a large V2 already.
Yes. So most of them are non-flow, but some of them are really flow, right?
Well, yeah, non-flow is weak, but in all small system publications, experiments have tried to remove non-flow, or at least reduce the majority of non-flow. Right. So and of course, believe what we measure is global, like a flow type.
I see.
This is hydrodynamic.
I see.
It's a global view. Yeah.
Okay, Hongxi.
So first, very interesting. Just wondering, like to compare this Quark-Gluon and the heavy ion Quark-Gluon plasma, is that we can have an initial condition in whether system like the initial conditions and to test whether this satisfies the hydrodynamic evolution.
So we can manufacture the initial shape, and depends on, so n equals to 3, probably we can triangle square possibly, but higher order probably not. So you mean that you want to see the V2 as a function of this geometry elliptical, triangular, square this is consistent with hydrodynamics, right?
Also, like for example, in Quark-Gluon plasma, so when that hydrodynamics can describe the data, and then from there we extract what is from there. And but the code, since we have about the and we conditions extract with code and whether the
well, and even the current RBBF, the interaction, the relation with
right
velocity, this is
right. So that's like to distance.
Someone, yeah.
With the magnetic field at the Fishback resonance, I believe it's something like a hydrodynamics because the opacity is really big, but when the magnetic field is lower, we are moving away from the resonance. The interaction becomes weak, but still non-zero, and we do observe V2. Now, I believe that's not hydro, because we can really calculate the number of collisions. We know the atom cloud very well. We know the density. We know the number of atoms. We know the interaction strength. Because those are all electromagnetism. So you can calculate, and you get average number of collisions to be say 0.5, 0.2. And at that point, I would say this is not hydro, because 0.2 would mean that the mean free path is larger than the size of the system by a factor of 5.
So it's with the increase the opacity, so the mechanism change from the escape from the from escape to the hydrodynamics.
Yeah,
so
I think I think it's a relative contribution. So it, and you still probably have some escape contribution, but it's small.
Remove experimental remove like what we did in the model. We can do the random randomize the direction of the patterns, and can do similar thing experimentally for the cold item experiment.
That's probably not possible. That's not possible. Yeah.
Okay, thank you for your answer and explanation. Thank you very much.
Yeah.
Okay, Yanni, please.
Okay, so can you hear me?
Yes. Yeah.
Thanks, Professor Chang, for the talk. I want to confirm, maybe I'm not aware of this. So you said you tune the Fishback resonance to tune the interaction. You always think the attractive part, or you also have some experiment data on the repulsive part?
Yes, we can also do the repulsive part. With positive scattering length. And the effect is similar. I think it's the same. So it also has interactions, and it really depends on the interaction. Yes, I believe so.
Okay.
It's attractive force or leaks, but it's for positive scattering length and a negative scattering length, the effects are the same. It depends on the cross section.
You should be assuming that the Quark-Gluon are more or less attractive.
Well, no, the scattering length, positive, negative, does not necessarily mean repulsive or attractive.
Okay.
Yes. If you get the let's see, when your scattering length is negative, then your force is, I'm trying to think. It's when the scattering length is negative, you do not have a, so if the force is negative or if the potential is negative, is attractive, you can get both positive scattering length and negative scattering length, depending on whether you have a bound state or not. With repulsive potential, you push the wave function out. I think your scattering length is probably always positive. Yeah. So yeah, I have to remind myself about the low energy nuclear scattering definition there. But the answer to your question is that so this does not matter. It's the interaction, the cross section that matters. Yeah.
Okay, Shushu, please.
And thank you for the nice talk. So for the rate data of V2O eccentricity, I noticed the data of 130 expanded synchronies. The data is extremely high. Do you have any clue? I think this plot using one from what was the synchrony?
Yeah. I think it's once I look into this, and I think it's the calculation of the eccentricity. So this is 130 GeV from early days of RIC. The calculation was not sophisticated. Thinking a smooth geometry and using parameter corresponding and eccentricity to be too small, and it yes,
eccentricity should be
That's a very energy independent. Yes, very weak dependence. Their eccentricity we could use the 200 GeV eccentricity. Yes.
Okay, more questions? Longam, please.
Hi, Fichang. I like this talk very much. So I'm wondering whether there is a way to study the quantum properties of these two systems, like the quantum fluctuations or the interactions that is related to the quantum property of those particles. For example, those boson and fermions, the difference between them, and also the difference between the liquid or fermions and bosons.
Yeah,
that's my question.
Thank you for the question. I have not really thought about this deeply, even though I kind of thought about this. My feeling is that we probably really have to go to very low density systems with only a few atoms, and maybe we will be able to quantum fluctuations because you have this, and it's easier to tackle that question. And then you can compare to in PP or PA collisions. But yeah, beyond that, I have not really thought about concrete ways to do that.
Okay, thank you.
Okay, more questions? Okay, if not, Professor Wang for the very nice. Thanks everyone and now disseminate. Thanks.
Okay, thank you all. And
Thank you.
talk to you later.
Bye.
See you later.
Bye.
Thank you.
Bye.
Bye.